Newton's first law of motion is inertia. It states that an object at motion tends to stay in motion, while an object at rest tends to stay at rest. This is shown here. Newton's first law explains why it takes additional force to start or stop moving through two different forces. These two forces are static force and dynamic force. Static force is when your body is at rest and must be overcome by a certain force before fluid movement can begin. This is the case when you push off the side of the wall. The resistance you feel when the movement starts is the static force that you overcome. As you can see here, the guy has to push off the wall before he can get going, but when he gets going, he will keep going.
Newton's first law talks about dynamic and static force, and basically what we can see here, as you see Zach get on the wall, he becomes at rest and has a very static force. And the outcome of that static force is when Zach pushes off the wall and he exerts a force of however large.
Newton's second law of motion says that force equals mass times acceleration. Newton's second law of motion explains why some people can swim at faster speeds than others. For example, if two swimmers have an equal mass and push off the side of the pool without taking any additional strokes, the person who used the greatest force when pushing off the wall will travel a farther distance. The acceleration in this situation was greater for the person who produced the greater force because the masses were the same. If you take these same two people and have them race to the other side of the pool, the person who wins the race would have to exert a greater force throughout the entire race in order to stay in the lead. A greater force produced by a person with a smaller mass will have the largest acceleration.
For Newton's second law, if two swimmers have an equal mass and push off the side of the pool without taking additional strokes, the person who has the greatest force when pushing off, like Zach here, you can see he's pushing off the wall, will travel a farther distance from the person who preceded the greater force because their masses were the same. Newton's second law discusses average forces and such, so we can find the overall force throughout a race that a swimmer exerts. So first, we're going to compare Zach with an Olympic swimmer. This is just average. We use some of Michael Phelps data. So first, you got to find the velocity that they choose, which is v equals distance over time. And you can see here, Zach, 2.1 meters per second. Average Olympic swim, or like the world record is 2.3 meters per second, which is pretty incredible. But then you take your velocity and you need that to find your acceleration. So you can see here we plugged in our velocity and then you get out your acceleration. You can clearly see that Olympic swimmer is better than Zach, clearly. But then when you plug it in to force, which forces mass times acceleration, you can see that clearly the Olympic swimmer is better than Zach, which would make sense.
Newton's third law states that for every action, there is an equal but opposite reaction. Through this law, Newton is describing exactly how movement occurs. For example, when you pull the water down your side using the butterfly swimming technique, the water moves down toward your feet, while in turn you are propelled forward. The action in this case would be you moving your arm in the water, and the equal reaction is the water pushing back on you. The opposition in this case, and many others, is the reason that the forward movement occurs. As you can see here, his swimming technique allows him to have force going towards the left, and the force of the water from the right is less than his force that he's creating, which allows him to go forward.
Newton's third law talks about different forces and how they react with each other. So we decided to do the butterfly stroke because it best shows this. So when you look up here, Zach is almost like pushing his arms back and pulling the water to his feet, which is propelling him forward, which is the force in this. And then at the same time, the water is pushing him back. And then for a problem, you would basically subtract the forces to find his final force of him being exerted.
Competitive swimmers don't just dive into the pool from the side. They start on the block called, appropriately enough, a starting block. The block lets swimmers push off with their rear leg at a 90-degree angle, optimizing the power of their start. So how does this connect to Newton's laws? Because it's all about acceleration. Let me start with a simplified case of a swimmer on a flat block. Even if the old style blocks weren't exactly flat, if the swimmer wants to dive off, he must push on the block to accelerate into a dive. Here's a diagram showing the swimmer and the forces on the swimmer during a start. Yes, the swimmer typically grabs the block with his hands, which I'll talk about in a moment, but for now let's consider the simple version. Now there are three forces acting on a swimmer: the gravitational force, the force of the block pushing up, and the forward friction pushing in the direction of acceleration. Remember, these are forces on the swimmer, not forces the swimmer exerts onto the block. Now let's assume that during the starting motion, the swimmer only accelerates horizontally with no vertical increase. In this case, the sum of the forces in the vertical must add up to zero. The basic principle of force says forces change the motion of an object. So since the vertical motion doesn't change, the net force must be zero, as seen in this equation. Now what about the horizontal direction? Believe it or not, there's only one force acting in the horizontal direction, which is friction. In almost all cases, the magnitude of frictional force, can be shown with the following equation, where mu is the coefficient of friction. It is a value that depends upon the two types of materials interacting by friction, in this case a human foot and a rough material on the surface of a block. The harder the two surfaces are pushed together, the greater the maximum value of the frictional force. The less than or equal to sign in the equation simply means this is the frictional force that tries to prevent the two surfaces from sliding. So, in the horizontal direction, the only force is friction, displayed in this equation. Now if the swimmer wants to win, he'll push right at the limit of maximum frictional force. This means you can use the maximum frictional force and reduce the problem like shown. So the maximum horizontal acceleration just depends on the coefficient of friction. I estimate a frictional coefficient of about 0.7, but it really doesn't matter what it is. Now let's talk about a block with a wedge. So what happens if there is a wedge at the back of the block? Again, let's simplify the situation just to show the difference. Let's assume the whole block is tilted at a given angle above the horizontal, which will just change the diagram to look like this. In this case, there are two forces that can accelerate the swimmer in the horizontal direction. Both the frictional force, as we saw on the old block, and the force from the block's wedge. If you write the net force in both the x and y direction, you get the following. Now it isn't so easy to see how this acceleration changes with higher wedge angles based off this equation, so I applied the maximum acceleration of angles up to 30 degrees. You can see it allows for greater acceleration off the starting block. Of course, this is just a model, since in reality, the swimmer only has one foot on the wedge and one on the block, but hopefully you get the idea. Now back to the hands. When a swimmer grabs the front of the starting block, it does two things. First, the swimmer can push with his hands as well as his feet for greater acceleration. Second, the swimmer also can pull up on the block. This increases the force that the block pushes on the swimmer and increases the frictional force, which in turn increases the starting acceleration.